All right, I know I said I wasn't going to record anymore, but the lack of a Monday class this week kind of threw my schedule off. So I want to record this for Monday, Wednesday. And then I'm not going to record it. All right, so any questions? ODPs, PA4. So let's know. All right, we're going to continue talking about heaps then. So remember our basic setup for a heap. So there's an example of a heap, right? All we need is each node is bigger than its children. No relationship related to left or right. And we can implement this on a computer the way we implement trees. We can use a structure that has a data and a left and right pointer. But we don't need to do that. Because this is always filled in, top to bottom, left to right, we can do the following. We can make an integer array in this case. How many did I go? 13, I can do that. And I'm never going to use element 0 in the array. That's just wasted space. But I'm going to fill in this array from left to right, top to bottom. So 100, 50, 75, 45, 43, 34, 16, 22, 21, 18, 19, 8, and 2. So suppose I store these numbers in an array. No pointers, no left child, right child, just a straight array stored in this order. It turns out this has all the information that we need to understand this set of data as a heap. So given a node at heap bracket I, its children are at heap bracket 2I and heap 2I plus 1. So suppose we're looking at the 45, which is stored at index 4. We know its children are stored at index 8 and 9, 22 and 21. Those are the two children of 45. And 34 is stored at index 6. Its children have to be 12 and 13. Children are 8 and 2. So from any node, we can find its children just by doubling the index and doubling the index plus 1. So we don't need pointers to find children of nodes. We can locate them in the array by using the index. And given a node at heap I, its parent, did I really put an apostrophe on it? Its parent is at heap I over 2, where we do this division as an integer. So node 34 was here at index 6. We saw its children were at index 12 and 13. Its parent is node 6 over 2 is 3, 75. 75's parent is at 3 divided by 2, that's 1.5. As an integer, that's 1. 75's parent is 100.
Its parent is at heap I over 2. Is that for the all of the children?
Any node.
There's 2 nodes.
There's a bunch of nodes.
So what I is that on the heap I over 2?
That's the node whose parent you're looking for. The parent of node I is node I over 2. Pick a node.
3.
3. So there is no 3 in our heap.
45.
45. Its parent is node 2. That's all it's saying. So 45's parent is 50. 45's parent is 50.
What about 43?
75? Wait, what should you say?
43.
43. 43's parent is 5 divided by 2, 2.5, that's 2.
Oh.
So 43's parent is 50.
We find 4.
Yeah, so as an integer. So we don't need pointers, we don't need back pointers. We can easily find a node's parent or we can find a node's children by just doing simple arithmetic on the index. Either double it and add 1, or cut it in half. And this solves the question if we simply have another integer variable that tells us how many things are in the heap. So heap size 13 means we have elements 1 through 13. If we want to add something to the heap, we add 1 to heap size and we store it at heap bracket heap size. Right? Heap size always tells us where the last element of the heap is. If we want to store another element, just add 1. That's where we store the new element. Yeah. If we want to remove the last element, the rightmost element on the bottom row, it's just element heap size. So remove that and subtract 1 from heap size. If you want to know if the heap's empty, check heap size. If it's 0, the heap's empty.
What was that adding one again?
So you want to insert, let's insert the number 46. So the first thing we had to do was we had to stick that onto the bottom row in the rightmost position, right? Well, to do that, look at your heap size, add 1, and then store your number at heap bracket, whatever heap size is, 46. And now we have to upheap. So we have to find 46's parent, that's going to be 7, and we have to compare that to its children, which is 14 and 15. Well, there is no 15 because that's bigger than our heap size, but we can compare 7 and 14. Those are out of order, so we're going to swap those. This will become 16, and this will become 47. 46. So we just did this thing. And now we have to check this node's parents and see if it satisfies the heap property. Parent of 7 is 3. 3's children are 6 and 7. So compare 75 to 34 and 46. It's bigger than both, satisfies the heap property, we're done. So you can code this up on a long bus ride, right? And there's no pointers, there's no null exceptions, there's none of the nasty mallocs. Right, assuming that you make a big enough array to hold it. And this is actually how we implement heaps sometimes, because it's just so much more efficient than dealing with the whole tree-like structure. And it gives you things for free, like what's the last entry. And if you want to find the largest thing in your heap, it's just heap bracket 1.
If you remove, don't you have to move a list?
Yeah, so you have to do a lot of swapping around of things. But the algorithm for it is pretty small. but you're gonna iterate log n times, right, for the height of the tree. So for 1,000,000 nodes, you might have to go through 20 swaps. It's still pretty inexpensive. So let's remove the largest. So what do we remove? The largest, that's always element 1. So that gives us 100. And then to take the rightmost element and place it in the root, we just take heap bracket 1, set it equal to heap bracket heap size. So heap size is 16, so change this to a 16. Decrement heap size by 1. So that's actually where our heap ends. And now we have to down heap. So 1's children are 2 and 3, and it violates the heap property. Take the largest of 2 and 3, swap that with 1. So we swap 1 and 3, so this becomes a 75, this becomes a 16. And now we compare 3 to its children, which are 6 and 7. So 16 versus 34, 46 violates the heap property. So swap with the larger of the children. So this becomes 46 and this becomes 16. And now compare 7 to its children, which is 14. 14's outside our heap. It has no children. We should be done. So if we had done this on our drawing, we would have put 16 here. 16 violates the heap, so swap with the 75. 75, 16. 16 violates the heap, so swap with the 46. And 16 now has no children. It's a good heap, and we're done. And this array still corresponds to our picture.
And what if you want to insert another like number larger than 75?
So let's insert 200. All right, so heap size goes up by 1. We put our 200 down at heap size, and we up heap. Want to do it in the array or the picture? Okay, it's easier on the picture. So look at its parent compared to the children. It violates the heap property, so swap 16 with a larger child. There's only one child, so just swap 200. 16. Check its parent, 46, violates the heap property here, so swap 46 with a larger child. This is 200, this is 46. Check its parent, 75, that violates the heap, so swap with a larger child, which is 200. There's 200, there's 75, we've got a heap. And if you think about the upheap process one step at a time, before we did this last swap, since we upheaped here, we know that this is a heap from this point down, which tells us that everything here is smaller than 200. And so if so everything here other than this new node was also smaller than this root. So when we swap these, we know that the root we're putting in here is going to be bigger than everything that's in that heap. So because we're doing this from the bottom up, we know that once we satisfy the heap property at this point, it's always going to be satisfied from there on down. So once you get to the root, we've got a good heap. And then this business we talked about yesterday of building a heap by simply throwing all your numbers into a heap and then going through and upheaping, right? That works really well with an array too, because how do you throw your numbers into a heap? Just drop them into sequential locations in the array. And now begin from here and move up and check each node compared to its children. And we know that if our last node is 200, down here at 14, well I didn't change this, but if our last entry is at 400, we know that nodes 8 on don't have any children. Because a child of 8 would be 16 or 17, and that's outside the size of our heap. So we know all of these nodes are childless, and the first node we have to actually check is node 7, which will have 1 child.
So this structure only inserts and removes the largest number.
It inserts any number and it only removes the largest number, correct?
I was just curious about removing like 43, but it only removes the largest.
Yeah, it's only gonna remove from the top.
How do you find the parent of 2 from the array?
The parent of 2, 13 divided by 2 is 6.5, so the parent is at index 6. This doesn't match the picture anymore, but that one still works. 34 is parent of 2. If I could call a data structure cute, it would probably be this. It's just something. All right. Other questions on heaps? Cool. Well, I am going to start talking about dynamic programming then, which is why I'm recording. So dynamic programming is really a way to speed up recursion, heavily recursive processes, to make them able to execute in a reasonable amount of time. The algorithms we're going to work with for even a modest sized problem will never finish if we don't use something like dynamic programming. Because the recursion grows so rapidly that for even a small sized problem, it's too complex to actually finish in the lifetime of the universe. So dynamic programming is going to be essential for writing code that's recursive but having it actually have a chance of executing and finishing. So I want to describe one of the problems that we can work on, that we can solve very easily recursively, but it becomes very complex computationally. And that's probably what we'll get through today, is looking at this first problem and beginning to look at its recursive solution. We won't actually get to the dynamic programming part yet, but this is a sample problem. And the problem is rod cutting. So here's the idea. You have a piece of metal, and it's got a certain length, and it's worth a certain amount. Right? It's metal, it's precious, people want it. They'll pay a certain amount for it. But chances are, people who are going to buy this piece of metal are going to want to cut it up into different lengths and use these smaller pieces for whatever purposes. So if you were to sell pre-cut pieces of this rod, you could get more money. Okay? So you're selling this piece of metal, but you're also offering to sell it pre-cut to certain lengths to try to get more money. And it turns out certain lengths are more valuable than others. For example, if you cut it down to little 1-inch segments, that's not very valuable, because most people don't want a piece of metal that small. So you get a little bit of money for it, people can melt it down, or they can sell it as a souvenir, but it's not terribly useful. But there may be a particular length that's very popular. And maybe everybody wants exactly an 8-inch piece of metal, because that fits a certain piece of your engine in a car. Okay? Plug in your favorite dystopian reality where all of this makes some kind of sense. So different lengths of material, different values. So the setup is you're given a table. So your table works like this: length and price. And these are the numbers I'm going to work with because they make it interesting. So let's just imagine this is an 8-inch bar, and you can cut it in any of these lengths that you want, and they command the following price. All right, so 1 inch bar is worth $1, 2 inches is worth $5, and 2 1-inch pieces is worth $2, right? But if you don't cut those 2 pieces, if you just give a 2-inch piece, it's actually worth $5. That's clearly more valuable. A 3-inch piece is worth $8, a 4-inch piece is only worth $1 more than a 3-inch piece. So if you got a 4-inch piece, you could sell it as a 4-inch piece and get $9, or you could sell it as a 3 and a 1 and get 8 plus 1 is $9. Or you could cut that 4-inch piece into 2 2-inch pieces, sell them each for $5, and now you got $10. So that's more valuable than just selling the 4-inch or selling a 1 and a 3. So the question is, if you have a stock of material, say 8 inches, how should you cut it in order to maximize the money that you can sell it for? Now a single 8-inch piece I can get $20 for. If I cut it into 8 1-inch pieces, I'm only going to get $8. That's not a good move. If I cut it into 4 2-inch pieces, I'm also going to get $20.
Well, where do you start from the maximum amount? Like, first you cut it into 6 inches and 3 inches. Since
So
$17 is the maximum, you'll start off from 6 or 7 inches. Cutting
So in some cases that will work, but we can actually set this up so that will not get you the best price. The problem with that is, in general, say that, and I haven't figured it out, did you already decide this is the most valuable per inch? Okay, you can go through and you can figure out which one is most valuable per inch. Okay, but because we can only cut it into an even, an integral number of inches, it may be that if we decide that a 7-inch is the most valuable, and then we're forced to sell the last inch as 1, it may be that a 6-inch one is slightly less valuable, but because we get an extra $3 out of a 2-inch as opposed to 2 1-inches, it might actually be more valuable to use a slightly less precious 6-inch cut and then throw in a 2-inch. So what you're describing is what's called a greedy algorithm. And there's some problems where a greedy algorithm works. You basically try to optimize your solution at each step. Now, if we could cut this into any length that we wanted, if it didn't have to be an integral length, right, we could simply find the cut that gives us the most value and make that cut, and then take the remaining space and find the most value we can get from that size and so on. And that will lead us to an optimal solution, but not when we've got integral lengths.
Can we use a graph that's like from 215, and instead of trying to find the shortest graph, try to find the largest?
So we can graph this out, and that's pretty much the solution we're going to head to. And it's complicated because once you decide you're going to do a 5-inch piece, now you've used up 5/8 of your material, you've got 3 inches left, and now you can either do a 3 or a 2 and a 1 or a 3 1s. But the number of possibilities grows really quickly. Right, so you can decide on the length of your first cut. And if your first cut is 1 inch, then you've got however many ways you can cut a 7-inch piece of material. If your first cut is 2 inches, then you've got however many ways you can cut up a 6-inch piece of material, and so on. So you can express the number of ways you can cut this in terms of the number of ways that you cut a smaller rod. And that's a complex calculation, but it's going to be an easy one to code.
Would rate of change go into here?
Oh, interesting.
Find the how.
Yeah, that would be an interesting way to do it. If you looked at rate of change from one length to another, I suspect there's a way to do that. I don't think it's obvious, but I think there's probably some interesting way to do that. Get into like a calculus of
something like this in microeconomics.
Yeah? Yeah, I can see that. So let's think about recursion. So you're asked to take over the shop for a day, and you got this 8-inch piece of metal, and someone comes in and they say, hey, you know, I want some metal, here's what I'll pay you for each piece, sell me some metal, and you gotta figure out how to cut up this 8-inch bar. And you wanna get the maximum profit, because it's your friend's shop, and they're gonna get mad at you if you don't make the best choice. And we don't know how to do this. But suppose we have a friend who has a business, and their business is selling 7-inch pieces of metal and cutting it up. And we have another friend who deals with 6-inch pieces of metal, and another friend who deals with 5-inch pieces of metal, and so on. Here's what we could do. So what's the maximum value? If we have an 8-inch rod, what's the maximum possible value we can get by cutting this up and selling? I can answer this if I answer 8 questions first. Okay, so answer the following. Question 1, how much do I get if I just sell an 8-inch piece of material? And that's easy to answer. I can look at my table, I get $20. All right, that wasn't a bad question. How much is 7 inches worth? Suppose I decide I'm going to cut 1 inch off and I'm going to be left with a 7-inch piece of material. I go to my friend who specializes in 7-inch rods and I say, hey, what's the most money you can get by cutting this up and selling it? And they come back with some number. Let's just call it max 7. Well, I know that I can cut it into a 1-inch piece and a 7-inch piece. The 1-inch piece will give me $1, and the 7-inch piece will give me however much my friend Max tells me they can get for a 7-inch piece. Which means if I make this cut at 1 inch, and then I let Max cut it up into little pieces for those 7-inch, this is how much money I can get total. Next question, how much is 6 inches worth? Well, I go to my next friend who's also named Max, and I say, hey Max, if I give you a 6-inch piece of metal, how much can you get for it? And they come back with a number called max of 6. And after I give them that 6-inch piece, I'm going to have a 2-inch piece left, which I can sell for $5. And I'm going to keep doing this. So if I cut it into a 5-inch piece, I've got $8 for my 3-inch piece, plus whatever I can get for the remaining 5. A 4-inch piece gets me $9, plus what I can get for 4. 5-inch piece gets me $10, plus what I can get for the remaining 3. A 2-inch piece gets me $17, plus whatever I get for the remaining 2 inches. A 1-inch piece gets me 17 plus 1 inch. And a 0-inch piece means I'm not going to cut it, I'm going to keep the original 8 inches for $20. And then add to that however much I can get by selling this 0-inch piece that's left over, which is going to be 0. Do I?
6 and 7, both have 17.
Yes.
No, I mean, X1 plus $17. Those are 1 inch plus 7 inches and 7 inches plus 1 inch.
But in this case, I'm keeping 1 inch. I'm turning 7 inches over to my friend to cut up. In this case, I'm keeping 7 inches and I'm giving my friend the 1 inch piece to decide how to sell. Yeah?
Or when you do like max 7 plus 1 no or max 6 plus 5 hours, would you want to do max 6 plus max of whatever's remaining?
You don't have to.
So say if you have like 5 inches left, you would sell it for $10, or you could sell it for 2 inches and 3 inches, which you get 8 plus 5.
Yes, all that I'm claiming here though is that if I cut it into 2 inches and I sell that as a 2 inch piece, and then I maximize how I cut the remaining 6 inches, this is how much money I'll get. I'm not saying it's the optimal way to cut off 6 inches and then do something with the other 2. I'm saying if I keep 2 inches intact, right, this is the most that I can get. If I keep 3 inches intact, this is the most that I can get. Okay, so this is keep 1 inch uncut. This is keep 2 inches uncut, and so on. So we've got 8 questions to ask. Actually, 9 questions. Yeah, this one kind of duplicates this one. If we know the answers to each of these questions, we can answer the whole question, what's the maximum possible value for an 8-inch rod? Because if we're going to cut this 8-inch rod and sell it off, the first thing we're going to do is we're going to make a first cut, right? And that first piece we cut is going to be either 0, 1, 2, 3, 4, 5, 6, 7, or 8 inches. If that first cut is 1 inch, then this is the most value we can get. If that first cut is 2 inches, this is the most we can get, and so on. Since we have to make a first cut, possibly, you know, of 8 inches, no cut at all, the most value we can possibly get from this whole procedure the maximum value we can get for 8 inches is whatever the largest of those numbers are. So we calculate these 8 values, and whatever calculation gives us the largest number, that's the most money we can get for an 8-inch piece of stock.
What is this algorithm called? What is an algorithm?
It's just a rod cutting algorithm. But it's a similar feel to what we'll see in other problems that we're going to talk about, like the knapsack problem or the egg drop problem or things like that. But it's a recursive solution, right? Because we're describing the maximum value we can get for 8 inches in terms of the maximum value we can get for smaller numbers of inches. So it has this natural recursive flavor to it.
What's the efficiency of this?
Horrible,
I would assume.
right? So, to calculate max 8, we need to calculate max 7, 6, 5, 4, 3, 2, 1, and 0. To calculate max 7, we need to calculate max 6, 5, 4, 3, 2, 1, and 0, right? We can write this whole thing out again. To calculate max 6, we're going to need max 6, 5, 4, 3, 2, 1, and 0. So let's make sure we're comfortable with this idea of an algorithm, and then let's look at its efficiency. So could we actually do this? Could we actually solve this problem and find what the maximum value is for 8 inches? Absolutely. But all we have to do is we have to solve these problems first. Right, well, max 0 is easy. If you don't cut, if you have no material, the most value you can sell it for is 0. Right, so max 0 is 0. So if you keep 8 inches of material uncut, you get $20. That's the most you can get. And we know that just from looking at our table. What's the maximum value you can get if you have 1 inch of material? It's just 1. So if you're going to keep 1 inch of material intact, then keep 7 inches of material intact, then you're going to get $17 for that 7-inch piece, and you've got 1 inch left, you're going to get $1 for that. That's 18 inches. If you're going to keep 6 inches of material intact, you're going to get $17 for that piece. And then what's the maximum that we can get out of a 2-inch piece? Well, max of 2 is the largest of either max of 1 plus how much we get for a 1-inch piece, or max of 0 plus how much we get for a 2-inch piece. And we already decided max of 0 is 0 and max of 1 is 1, so this is $2, this is $5. So max of 2 is $5.
So when we find max, we need to find all the possible combinations and cut into the pieces
Yeah.
and compare the prices.
Mhm. Now, I'm kind of doing something sneaky here. I'm working from the bottom up. And this is actually a pretty efficient way to do it. So let's find max of 3. So max of 3 is the largest of the following. If we keep 1 inch uncut, it's going to be max of 2 plus the value of a 1-inch piece. If we keep 2 inches uncut, it's going to be max of 1 plus the value of a 2-inch piece. And if we keep all 3 inches intact, it's max 0 plus the value of a 3-inch piece, which is 8. And I've already calculated max of 0, 1, and 2. Max of 0 is 0, max of 1 is 1, max of 2 is 5. So this is 6, this is 6, this is 8. So the maximum value we can get is $8. So we're making progress here. And we can just keep working our way up. Right, max 4 will be the largest of max 3 plus 1, max 2 plus 5, max 1 plus 8, or max 0 plus 9. And it's not bad, it's an order n squared work, because we're starting from 0 and working our way up. But typically when you're using an algorithm like this, you don't start from the bottom and compute every value going up. You start with the question of what is max of n. And that looks a little different. So to compute max of 8, I need to compute the following. Max of each of those. To compute max of 7, I need to compute each of those. 6, I need to do these. 5, I need to do these. I my tree's getting really wide really fast.
Let that at 0 on 4.
Say what?
Let that 0 on 4.
Yeah, it did. Thanks, now my phone's even worse. And I'm not going to draw this in its entirety, but just take a look at this. Right, I can't even fit that first leftmost branch on the board. And that's just coming off of the 6, and I've got something almost as big coming off the 5 and the 4 and the 3, and that will just get me the 7 branch, but I'm going to have all of that repeated over here under the 5 and the 4 and so on. And this is just for max of H. If you try to do max of 50, you got a big problem.
Can't you cut out a lot of that recursion though by just storing the max values for certain ones in an array?
That's dynamic programming. So that's exactly what we're going to do. Because once I compute max of 4 right here, I don't need to recalculate it here. If I save it somewhere, instead of going down this whole tree and figure out what max 4 is again and again and again, each of these, I can just read it out of memory. And in fact, I'm never going to need to do these because up here, when I try to find max of 4, if I've already calculated it here, I can save that value. And now to find max of 50, I'm going to need about 50 calls to my max routine. Because the first time I find max of any given number, I'm going to save it in memory. And when I call max and say, what's max of this number, the first thing I'm going to do is look at my memory and say, have I already been here before? If I have, I'll just read it out of an array. If I haven't, I'll go ahead and I'll use this whole algorithm to calculate the value. And then before I return, I'll save it in my array. So the next time it's there, I don't have to recalculate. And while I'm calculating that value, each of these calls to max will do the same thing. Before I calculate max 3 recursively, I'll say, is this already calculated in my array? And if it is, I'll just read it out. And if it's not, I'll do the calculation, and at the end, I'll save max 3. And now the next time I need max 3, it'll be there. And this is just huge speed up.
This is kind of tangent to this, but I did a similar thing in AST parsing.
Okay.
I had no idea what it was.
Okay.
I didn't realize it was so applicable. It's
Interesting.
Like this exact same thing.
What's it called?
AST parsing. Like
Okay.
A programming language.
Yeah.
And I was realizing, okay, I don't want to parse these whole things again, and it's this exact same thing.
Cool.
So it's applicable to a lot of
Nice.
things. They're not just numbers.
Yes, it's a general concept, and it's very applicable. And it goes directly to why this is so expensive time-wise. And you can use it for all kinds of recursive processes. So another example is computing Fibonacci numbers. So if you want to compute the 8th Fibonacci number, we know it's just the sum of F7 and F6. Right? So Fibonacci, the nth number, is the sum of the two numbers before it. Right? So it's this sequence. And it's tied to sunflowers and pine cones and others, and other things. So to find F8, all we need to do is calculate F7 and F6. If we just write this as a straight recursive function, when we try to calculate F6, it's going to try to calculate F6. F7 is going to calculate F6 and 5. And usually we just hardwire F1 and F2 to be 1. That's our base case that we return without recursion. So once we get down to a 2, we don't have to recurse anymore. But the 3 will be a 2 and a 1, the 4 will be a 3 and a 2, which will be a 2 and a 1, the 5 will be a 4 and a 3, the 4 will be a 3 and a 2, the 3 will be a 2 and 1, and so on. You get the idea. And then we have all of this stuff sitting here under the 6. And And Fibonacci's blow up pretty quickly too. If you try to figure the 1,000th Fibonacci number using this, it just sits there and spins.
Can be used for finding primes too.
Yeah?
Yeah.
Yeah, same idea,
generate
storing
lookup.
primes instead of recalculating.
Yeah.
Yeah, so like what some people do with Goldbacks at 215. General idea, right? Store these results once you calculate them, and then next time you have to calculate them, check to see if they're saved first. We do this as people, right? This is what our brains do. We don't relearn something again and again, right? We learn shortcuts. So when we calculate the derivative of x squared, we do x plus delta x minus x divided by, and so on and so forth. But once we've learned that the derivative of x squared is 2x, the next time that we're doing something and we need to take the derivative of x squared, we just plug in 2x, right? That's really all that's going on here. Never forget how to do it during summer break.
So like in C specifically, if we have like, we're trying to find a max of 50, does that mean in our recursive function, we're gonna be now allocating like 50 items, or are we, assuming it's dynamic, so?
Yeah.
Okay.
So, and in general, if you get a programming assignment for this, I'll say something like, the maximum rod length is 1,000. So you just say integer cost bracket 1,000.
So
You don't
3 is
even
very
need
good in
it.
that situation.
Yeah. All right, so that's one example of dynamic programming. Monday, we'll talk about a similar problem called the knapsack problem. And the knapsack problem, we can look at greedy solutions to that. We can look at why greedy solutions don't work if you have items you can't cut up. And we'll see different ways to go that. All right, so we'll do that Monday. Club meeting in 10 minutes. I'll see you there, or I'll see you next week.